An old way to specify different carbons is to use the Greek alphabet. In this designation, we first need to identify the functional group. So in our case, the carbonyl group is our functional group. The carbon right next to it is called alpha. The next one should be beta, and then gamma, and so on. On the other side, if you have a carbon here, this carbon will also be alpha, then beta, and so on. There's a property of aldehydes and ketones that is relevant to our succeeding topic. This is acidity. It's known that the hydrogen attached to the beta carbon has a pKa that is very high, around 40 to 50. It means that this hydrogen is difficult to remove. However, the alpha hydrogen, the hydrogen attached to the alpha carbon, has a pKa of 19 to 20. This is very unusual. This is also the basis of Keto-enol tautomerization. These tautomers are constitutional isomers that are easily interconverted by a trace of acid or base. Your base can readily take this proton because it's acidic, and it can form your carbon ion. The lone pair is in this carbon, right next to the carbonyl. Through the localization, this electron can form a double bond, and this will become a single bond. We have here a species we call an enolate. This enolate can be protonated to form your enol. The carbon ion and the enolate will form a hybrid. This hybrid contains partial charges on oxygen and on carbon. If protonation occurs on this side, you will get the keto form, and if protonation occurs on this side, you will get the enol form. However, because the carbonyl double bond is stronger than the alkene double bond, the keto form is the major isomer, and the enol form is very small in proportion. While most aldehydes and ketones primarily exist in the keto form, beta-dicarbonyl compounds exist primarily in the enol form. Beta-dicarbonyl are named as such because if we take this as our reference, this carbon is alpha and this carbon is beta, so beta-dicarbonyl. Because there are already two carbonyl groups present, this proton can be easily removed and you form an enol, and this enol has a hydrogen. This hydrogen can form a hydrogen bond with this oxygen. This is the major driving force why your enol form is the major isomer. Take note that because of the two carbonyl groups present, the acidity of this hydrogen becomes much stronger. The first reaction that makes use of the acidity of the alpha proton is alpha-halogenation, or the formation of haloforms. In the presence of a base, this proton can be removed, and once removed, it can be replaced by a halogen, such as in this case here. Multiple halogenations can occur as long as you have a hydrogen that can be replaced. For example, we have here acetone. Your base can remove this proton. You will form an enolate. This enolate can interact with a halogen such as iodine. We can also use bromine or chlorine in this case. So the interaction will, in effect, replace your hydrogen with a halogen. There are still hydrogens here, and because you added a halogen at this carbon, these hydrogens will become relatively more acidic than these hydrogens here. So, a hydroxide can take all of these hydrogens and replace it with iodine. In this instance, further interaction with the hydroxide can enable the cleavage of this bond. The cleavage can generate a carboxylic acid and a carbon ion. This carbon ion is a strong base, and it will readily take this proton to form your halo form. The halo form is like this: CHX3. Our case here is iodine, so this is called iodoform. If this is chlorine, we call this chloroform. If bromine, it's called bromoform. And the side product is your carboxylic acid. One useful property is that this iodoform has a yellow color and can be used to test methyl ketones. In acetone, you have a methyl group attached to the carbonyl. And if you have a methyl group, you will get a yellow color upon reaction with iodine and hydroxide. This can be used in an iodoform test. This can indicate the presence of methyl ketones because iodoform forms a yellow precipitate in solution. That is, if you have a sample of your methyl ketone and you mix with your reagent, iodine, you will get a yellow precipitate, indicating the presence of methyl ketones. Alkylation is possible because of the acidity of the alpha protons. A strong hindered base, such as lithium diisopropylamide, favors the kinetic enolate. Lithium diisopropylamide, it has this structure. It is hindered because of the isopropyl groups right next to the nitrogen. If there's a hydrogen here, this hydrogen would be hard to remove, so once removed, you will get a very strong base. For this example, you have two locations where protons can be taken. These positions can be differentiated by LDA because here it's much more exposed, while this is sterically hindered. Because LDA is a very big base, it is very likely that it will take a proton at this side and form the enolate here. If we have a weak and small base, like this, it can take a proton from here or here with ease. And the formation of the enolate will depend on the stability of the formed enolate. A double bond here compared to a double bond here. Because this will be more substituted, the double bond here will be much more stable. That will be our thermodynamic enolate. A kinetic enolate is different. The proton is removed from a less hindered alpha position, here. Once this is formed, you can mix it with primary, benzylic, and allylic halides to enable alkylation. On to aldol reaction. Aldol reaction is the enolate addition to carbonyl. Consider the reaction of these two ethanol molecules in the presence of 10% aqueous sodium hydroxide. The end result should be this compound. This compound is an aldol. You have an aldehyde group and an alcohol group. That's why it's called aldol. How does it happen? You can use acidic or basic solution to afford the aldol. This base can take this proton and you can form your enolate. Once you have your enolate, it can react with another molecule of your ethanol. The attack can occur at this carbonyl-carbon. You will get your alkoxide. Take note that you already used two equivalents of ethanol in this case. It only requires protonation here with water, for our case, and we will get your target aldol. If heated, dehydration to an alpha-beta unsaturated carbonyl compound takes place. This is a condensation reaction. Using acetone in an acidic environment, the enol will form. This enol can form the double bond and then attack this carbonyl-carbon. You will form your aldol. We call this an aldol reaction. If you heat it further, in the presence of an acid, this OH will be protonated. Now you have a good leaving group and an elimination will occur very easily. This is an alpha-beta unsaturated compound, the alpha carbon and the beta carbon. And once the water is removed, we have here a condensation. The reaction is called aldol condensation. All the examples that I have shown you so far involves identical molecules of aldehydes or ketones. What about if you use different molecules of aldehydes or ketones? I use here, for example, two different aldehydes. This is propanol, this is ethanol. In the presence of our base, there are two possibilities where you can take a proton, here and here. This will allow for you to form this compound. If you take a proton from here, you will get an enolate from this compound, and this enolate will attack this carbonyl group to form this structure. There's another instance where you could take a proton from here. It will form an enolate. This enolate will attack this carbonyl group, and you will get this structure. We call this reaction cross-Aldol reaction because it involves two different molecules as starting materials. There's also another way wherein the same molecules will interact with each other, and we call those self-Aldol reactions. There will be two products in that case. So overall, if you mix these two compounds together with hydroxide ion, you will get four different products. And different products formed in such a reaction will be difficult to separate. Despite these challenges, there are methods available where you can do cross-Aldol reactions. You can do selective deprotonation by a strong hindered base to form the kinetic enolate, such as the case for LDA. So here you have two possibilities. The proton may be taken from here and the proton may be taken from here. But LDA is a hindered base, and in this case a very low temperature is used to enable removal of the proton only at this location. This enolate will be formed selectively and not this one. If another aldehyde or ketone is added to this enolate, only a single product is expected. Subsequent protonation will give the Aldol product, only this one, obtained in 75% yield. Another method that is typically used to allow cross-Aldol reactions is to use reaction partners where one of the reactant has no alpha hydrogen and the carbonyl with alpha hydrogen is added slowly. Example of a compound that has no alpha hydrogen is benzaldehyde. Here, there are no protons that are alpha to the carbonyl. Benzaldehyde is mixed first with the base, and then another compound which has the alpha hydrogen is added slowly. Here, acetone only has one type of alpha hydrogen, either this one or this one, they are equivalent. And if you take a proton at one of these carbons, you will form your enolate, and this enolate can attack here to form the Aldol reaction product. There will be no other reaction products here. Further reaction may allow dehydration and the formation of a double bond here to form this compound.